All right, as with all modelling, let's have a good read of the question and draw a diagram if we can. So we've got a rectangular block such that the sides of its base are of length x and x, or x and 3x I should say, and the sum of all the edges is 20. So x, 3x, so there's the base dimensions. The height of the box, I'm not too sure, so I've put y. Yeah. All I do know is if I add up all those edges, I should get 20 centimeters. So if I add up all the edges, clearly there's 4 y values. I've got 4 lots of 3x and I've got 4 lots of x. So if I add all those up and rearrange, I get a relationship between y and x. So the length or the height of my box, if you like, y is given by 5 minus 4x. So then if I just work that into the volume equation, which is length by width by height, and I know the dimensions of my box are x by 3x by y, and y is 5 minus 4x, I end up with 3x squared times 5 minus 4x. Should have that bracket closed. And that gives me 15x squared minus 12x cubed, which is what I was expected to get. Okay, so with any sort of a show instruction, it's really important that you don't use the expression that you're trying to show in any way, shape, or form. You do all your calculations, and then your final answer should be what you're trying to show. Okay. All right, find the derivative dv dx. So if I just differentiate that, I get my 30x minus 36x squared, so that's good. Now, find the local maximum for the graph of v against x over the maximal domain. So it's important, you've got to calculate a sketch your graph, okay? So if I sketch the graph, it's a negative cubic, so I know roughly what it looks like. And clearly my volume is going to be positive. My x value, which is a length, is also going to be positive. So I'm only interested in this top right-hand corner. So that's the graph over the maximal domain. If I use my calculator or solve to find my x-intercepts, I work out that that x-intercept occurs at 5 on 4. All right. So to find a local maximum, I need to find where the gradient is 0, which means I find dv dx equal to 0. So if I solve my derivative equal to 0, I get the points x equal to 0 and x equal to 5 on 6. So they could be a maximum, they could be a minimum. So from the graph, you can probably infer which one's going to give the max. But if I put x equal to 0 into my volume equation, I get 0. So that's the minimum value at 0, 0. And if I put x equal to 5 on 6, look, if we've got a calculator, just use your calculator. A little bit of manipulation in one way, shape, or form will lead us to 125 on 36. But with all modelling, we've typically got our calculator available to us. So we just get that 125 on 36. Now, because it hasn't given us any decimal accuracy, we have to give an exact value. So it's important we work out the exact value, not a decimal point, not tracing it on our calculator, just getting a decimal. So the local maximum, 125 on 36. All right, say my domain has been restricted now to be between 0 and 4/5. Okay, find the absolute maximum of v and the value of x for which this occurs. So the absolute maximum is just the maximum value of the function. Okay, where does the maximum occur? If my graph was extended all the way, I'd have this part out here on the negative side, and my maximum would be where x is equal to negative something. Yeah. So I'll just erase that. All right, so where does 4/5 sit in relation to 5/6? Now 4/5 is actually less than, okay, it's less than 5/6. So my 4/5 is around here somewhere. So the maximum is just going to occur at 4/5. So if I put 4/5 into my volume rule, again, work with your CAS, I get 432 on 125. So that's where the maximum value is if I restrict the domain. If x is between 0 and 1, find the absolute maximum. Well, 1 is obviously probably wrong pen. 1 might be the point there somewhere. Okay, so my maximum is going to occur where the local maximum is, and we've worked that out already. So the maximum occurs at the local maximum, which is at x equal to 5/6, and that maximum volume we worked out previously to be 125 on 36. All right, so there's a couple of parts about this question. One, whenever we have a show, we can't use that expression. We can't use the v of x expression, all right? It's there. If we wanted to be nasty about it, we could just say, find the equation of the volume. And then if you can't find the equation, you can't do any of the question. So instead we say, right, this is the volume equation. Show me how we got that. All right. And then we're just distinguishing between a local maximum and an absolute maximum. All right. Local maximum, turning point. Absolute maximum, just the biggest value on the whole function regardless. All right. And we can see just from the CAS printouts there, find the derivative. Okay, solve the derivative equal to 0. There's my maximum or minimum. Okay. If I substitute 5/6 into that equation, I get 125 on 36. If I restrict my function to be between 0 and 4/5, okay, the maximum occurs at 4/5, so I could use a function maximum feature. Don't forget you've got to put the variable x in. And then if I put x equal to 4/5 into my rule, I get the 432 on 125. All right, off you go.